In today's lesson, we'll be looking at the two main types of energy. All types of energy can be broken down into two main types, what we call potential energy and kinetic energy. Potential energy is energy that is stored up in some form. Potential energy is the energy an object has due to either its state or position. What do we mean by state? Well, in a compressed state, a spring has potential energy stored up inside it that it can release at a moment's notice. Or in an elongated state, it has also energy that can release by contracting back again. If it's a rubber band that is all wound up, it has that pent up or wound up energy that it can release all of a sudden. What do we mean by its position? Well, if we have an object that is placed up high, then if it all of a sudden starts falling, it can do work. So we say that it has energy that was stored up because of its high position. So all of those are examples of where you have potential energy. What is kinetic energy? Kinetic energy is the energy that an object has because of its motion. So anytime an object is moving, it has kinetic energy. So all forms of energy can be broken down into either one out of those two types. Heat energy, that is considered movement of motion. Anytime the atoms in an object are moving, it is considered the heat energy of that object. Chemical energy, like the kind that is stored up inside you that you ate, that is considered potential energy. Mechanical energy, that is the energy of the moving parts of a machine. Elastic energy, that is the energy that is stored up in an elastic band or a spring. Electrical energy, that is the energy of moving electrons in a wire. Nuclear energy, that is the energy that is stored inside the core of an atom. So because I know of physics, I don't like to think of myself as overweight. I am just bursting with chemical potential energy. So now let's take a look at this clip from Bill Nye that just illustrates how energy can change from potential to kinetic and back and forth.
And energy can be converted from one form to another. Energy is what makes things go, run, or happen. So let's make something happen. Say with this big box of water. See, when we filled this box, we lifted the water up here. And when we did, we gave it some energy. Think about it. You have to work to lift a bucket of water. So when you lift it, the energy of lifting is stored up here. I'll prove it to you. When we open this valve, water flows downhill and runs this little propeller. The propeller spins and runs a little generator which makes a small amount of electricity. It runs through this wire and makes this needle move. Some of our electricity is made by falling water at huge dams that have huge propellers. When energy is stored, we call it potential energy. It has the potential to do something. When it's moving, we call it kinetic energy. Kinetic means moving. Now this setup converts the potential energy that we put into the water by lifting it to a form of kinetic energy, the energy of the flow. And the flowing water makes electrical energy. Kinetic energy was converted to electrical energy. Energy was changed from one form to another.
Thanks, Bill. Now, let's derive the formula for gravitational potential energy. Let's recall that work is equal to force times distance. Now, gravitational potential energy is the energy an object has due to its position. So if we take an object and we lift it up and put it somewhere high, we have done work by transferring our chemical energy into gravitational potential energy stored within that object. How do we calculate it? Well, the amount of force needed to raise that object is equal to the weight of the object. Let's recall that the weight of an object is its mass multiplied times the gravitational field strength. Or in other words, W is equal to mg. What distance does it move? Well, it moves from the ground up to the height that you have placed it. If we substitute those into our formula here, we get that the potential energy is equal to the mass times gravity multiplied by the height h. Simplifying by simply removing brackets, we get that the potential energy is equal to mgh. Now, let's derive a formula for kinetic energy. Again, remember that work is equal to force times distance. Now, let's recall that force is equal to mass times acceleration. Also, let's recall our formula for acceleration. Acceleration A is equal to v minus u over t. What distance does it move? Well, let's recall our formula for displacement. S is equal to 1/2 u plus v times t. If we substitute those into our formula, we then get that the kinetic energy is equal to the mass times v minus u over t times 1/2 of u plus v times t. Simplifying this equation, we notice that the t's cancel, and we're left with 1/2 m times v minus u times u plus v. But if we look at expanding v minus u times u plus v, you should see that those are a difference of two squares. So expanding v minus u times u plus v, you get v squared minus u squared. So we have our formula 1/2 m times v squared minus u squared. This is the formula to find the change in kinetic energy. But if we consider that our object started from rest, where the initial velocity u is equal to 0, then that means that our formula is simply the kinetic energy is equal to 1/2 times mv squared. Now, let's go to the other Mr. Physics explaining some problems of calculating kinetic energy and potential energies and the two of them meshing together. Hey, thank you, Mr. Physics. You know, you're an okay guy. Yeah. All right. So, let's look at this example, girls. We know that a brick of mass 5 kilograms is lifted to a height of 1.8 meters above the ground. So, we are to determine the potential energy it possesses, taking gravity as 10 newtons per kilogram. Then, let's say the brick falls. Immediately before it hits the ground, how much kinetic energy will it have? And you are to use your answers above to calculate how fast it will be moving as it hits the ground. And finally, why in reality would the velocity be less than calculated? So let's begin by identifying our givens. We know that the mass is 5 kilograms. The height is 1.8 meters. And gravity is 10 newtons per kilogram. Our formula for potential energy is mgh. Substituting those values, we have 5 kilograms multiplied by 10 newtons per kilogram times 1.8 meters. The kilograms cancel out and we're left with Newton meters as our units, which is the same as joules. So our answer is that the potential energy is 90 joules. Next part, how much kinetic energy would it have when it hits the ground? Well, according to the principle of conservation of energy, energy is neither created nor destroyed. It only transforms from one form to another. So as that brick is falling, it is losing potential energy and it is gaining kinetic energy. So our assumption here is that at the bottom of its journey, right before it hits the ground, then it is going to have lost all of its potential energy and only possess kinetic energy. So the potential energy that it previously had is now equal to the kinetic energy that it now has at the bottom, just before it hits the ground. So the answer is simply 90 joules. Next, let's see. We want to calculate the velocity just before it hits the ground. So let's identify what we know. We know that the mass is 5 kilograms. The amount of kinetic energy it possesses is 90 joules. Our formula for calculating kinetic energy is 1/2 mv squared. Substituting the values that we know, the kinetic energy will be 90, the mass is 5. Simplifying, we'll have that 90 is equal to 2.5 v squared. Transposing and dividing 90 by 2.5, we get that v squared is 36. So then to find v, we do the opposite of square, which is square root, and we get that v is 6 meters per second. Now, why in reality would it not be 6 meters per second, but in actuality less than that? Well, because we have not taken into account air resistance. In reality, air resistance would slow down the brick. And that is our lesson for today.